we want to talk about surfactants, or soap and detergents. This is really a carryover from our previous lab where we were talking about nonpolar and polar molecules, which leads us to soaps and detergents. Why does it lead us to soap and detergents? Observed that oil and water don't mix, but yet we all know that we use oils and fats in our cooking, and we have to get them down that sink somehow. So what do? We use soaps. Right? One drop of Dawn gets the whole wash clean. What is it about Dawn chemically that allows the grease and the fats to dissolve into water and to go down the drain? Let's take a look. Chemically, let's define our problem. How do you get oil and water to interact? Remember that oil is nonpolar. And it will only talk to other nonpolar molecules. Water, on the other hand, is polar and will only talk to other polar molecules. So how do we get the two to interact? Good question. What we need is a translator molecule. We need a molecule that will interact with both. In essence, we need a molecule that is both polar and nonpolar. How in the world can we have that? How in the world can we have a molecule that's both polar and nonpolar? That's where our detergents come in. Alright, so what molecule exists that can translate the language of water into the language of fats? You know the answer. That's soap or detergent. Whenever we want to get our fats and our oils and our greases dissolved into water, what do we use? We get some soap or we get some detergent. Both of these molecules bridge the gap between polar and nonpolar molecules because they're capable of living in both worlds. Let's take a look at the simpler of the two here. Let me pull up my soap. This is a molecule of soap, and what you can see is that you have a really long chain of carbon and hydrogen. And that long chain of carbon and hydrogen, you'll remember, because it consists of carbon and hydrogen, is nonpolar. So you've got this big part of this molecule that's nonpolar. In other words, it's going to interact with your fats and your greases. Then down here, you have carbon bonded to 2 oxygens. This carbon bonded to 2 oxygen, guess what? That area of the molecule is actually polar. So what you have with a soap is you have a nonpolar tail and a polar head, so to speak. So this part of the molecule is capable of interacting with your fats. This part can interact with your fats. This part can interact with your polar molecules, such as water. So what happens is you place your detergent into your mixture of fats, and these soap molecules wedge themselves along your fat molecules. And then they'll have the other end of them associating with some water molecules. And you'll sort of have this three-way interaction, or this three-way bond, where you've got one end where you've got the grease interacting with the soap, interacting with the water. And that allows all of them to mix together. Detergents are the exact same way. Detergents, once again, you have a really long nonpolar tail to interact with your fats, and you have a, well, the benzene's really part of the, let me kind of switch that up here. There we go. And you have a polar end capable of interacting with water. The big differences between the two is a detergent usually has a sulfonate group out here, whereas a soap is usually a carbolic acid. If you've gotten to the organic chemistry part, it's really the difference between a detergent and a soap is a soap you have carbon bonded to oxygen to provide your polarity, and in a detergent you have a sulfur bonded to oxygens to provide your polarity. And that's really your difference between your soap and your detergent. Because they're able to do that interacting with both groups, they can get the two groups to mix with each other. And that's how we get that grease and the water to mix together and to go down our drain. Now, this has some really, really interesting properties when it comes to what goes on the surface of our water. If you've ever looked at a really, really full glass of water, and I mean, get a glass of water, fill it all the way to the top, and then very carefully add a few more drops in. So I've got my glass of water here, and I keep adding water very carefully. If I then look at the top of my glass of water, what I'll notice is that on the surface of my water I have a little bit of a dome. Right? I have an area where I've overfilled the cup, but yet somehow I've got what looks like water sticking up above the cup over here. This phenomenon that you're seeing is caused by something known as surface tension. Remember, we said that water molecules are interacting with each other. That water molecules experience a force of attraction for each other. Well, the force of attraction between water molecules usually goes out in all directions. Right? If you have a water molecule let me see here. Oh, what am I thinking? Write down Kermit the Frog. Write down Kermit the Frog. All right, if you have a water molecule here in the surface of your glass, then it's exhibiting a force of attraction to water molecules above, below, next door, in front, and in back of it. So it's got its force of attraction, or its hydrogen bonding, going out in all sorts of different directions. Up here at the surface of the water, however, each water molecule has just as much love to share, just as much force of attraction to share as the water molecules in the center of the cup. However, they don't have any water molecules up here, right? There's no water molecules up here for them to interact with. So their force of attraction can only be spread in the downward direction and in the side-to-side direction. So at the surface of the water, the same force of attraction that you find in the center of the water is spread over half the number of molecules. So if you take the same amount of force and spread it over half the amount, you're going to create a stronger bond, right? And that added strength that you find at the surface of the liquid between the molecules of water is the property we know as surface tension. I'm going to give a definition of surface tension that's probably making some pea chemists throw up a little bit, but I'm going to go ahead and give it anyway. It's the strength or the extra strength of surface tension is the extra strength of intermolecular forces that you find at the surface of a liquid. You can see this very easily if you ever, well, you know what, I'll see if I can't shoot a video here in a few seconds for you. But I digress. Let's move on. Write down gonzo. Write down gonzo. G-O-N-Z-O. Gonzo. Gonzo the Great. So what does surface tension have to do with detergents? Why are we bringing it into our conversation? Well, we have a bunch of water molecules here, and they're experiencing surface tension. When we add soap molecules to our water, those soap molecules come in here, and they begin interacting with some of those water molecules. Well, in order to interact with those water molecules, they have to break the interaction the water molecules were having with each other. So these detergent molecules or these soap molecules weaken the surface tension and the intermolecular forces between the water. Anything that does that is known as a surfactant. So surfactants or detergents not only help water interact with fats, but they weaken the inability of water molecules to associate with each other. They lower the surface temperature by getting in there between them. You can think of surfactants as the third wheel on the date between two water molecules. They're attracted to each other, they want to get along with each other, but somebody bought this detergent molecule along who won't shut up during the date and somehow winds up sitting between the two of you during the movie. Wait a second. Maybe that means I'm actually the third wheel on the date. At any rate, I digress. In today's lab, you're going to actually witness the ability of detergents to bridge the communication gap between fat and water. Now, if only we had a source of fat dribbled throughout a bunch of water. Oh, wait, we do. It's called milk. So in today's experiment, you're going to take some milk, and milk is a bunch of fat suspended in water. Remember, water and fat can't mix. So what's happened is your milk contains fat that's suspended, sort of like carbon dioxide bubbles are suspended in water. They form those little, what's known as micelles, or little globules inside the water. But your milk and fat is basically a bunch of little balls that you're not really able to see. It's surrounded by some proteins in the milk that kind of help those little fat globules in your milk interact with the water. So there's already some translators present in the form of some proteins. But milk is basically water with a bunch of fat suspended in it. So what you're going to do is you're going to take some food coloring here and place it in the center of your milk. And then you're going to add a few drops of detergent to it. What's going to instantly happen is that soap is going to be attracted to not only water molecules, but it's going to be attracted to the fat, right? Half of that soap molecule can interact with water, but the other half of that molecule has to be able to find a fat to interact with. So those soap molecules are actually going to go and move about quickly from wherever you drop them in, and they're going to race around trying to find fat. And as they race around and try to find fat to join up with, those soap molecules are going to drag some water molecules along with them and drag along the food coloring that's interacting with the water molecules. So hopefully you'll see a really groovy tie-dyed pattern sort of develop in your milk when you perform the experiment. So you're actually able to see the soap go out into that dance club of your milk solution and try to find some fat to hook up with, illustrating soap's ability to interact with both polar and nonpolar substances. Why don't you write down Stanley? Everybody write down Stanley. Couple things I want you to do is I want you to try this experiment 3 different times. I want you to try it once, not using milk. Just try it with water and your food coloring and your detergent and see what happens. 2, try it with 1% milk, and then get a small thing of whole milk. So try it with water, 1% milk, or 2% milk, whatever it is you drink in your house. and then try it with whole milk. Video at least one of the milks and tell me what differences you observed between the three, and why you observed those differences. And that's it!